Okay, feeling pretty lucky. Just lucky I have this textbook and I can read it like this. So anyways, the first page says section 1, theory of heat, and then the second page says unit 2, matter and energy. Okay, I get it. So 2.8, conservation of energy. The law of conservation of energy states that energy can be neither created nor destroyed, but can be converted from one form to another. It can thus be said that all energy can be accounted for. Most of the energy we use is a result of the sun's support of plant growth for millions of years. Fossil fuels come from decayed vegetable and animal matter covered by earth and rock during changes in the Earth's surface. This decayed matter is in various states, such as gas, oil, or coal, depending on the conditions it was subjected to in the past. Figure 2.13. Gas and oil deposits settle into depressions. Then, it shows like the Earth's surface, then soil, rock, gravel, sand, rock, more rock, then gas, then oil at the very bottom. The energy stored in fossil fuels is called chemical energy because a chemical reaction is needed to release the energy. A battery is an example of a device that changes chemical energy into electrical energy. 2.9, thermal energy. Temperature is a measure of the degree of heat or the heat intensity, but not necessarily the amount of heat. Heat is a form of energy because of the motion of molecules. To be specific, heat is thermal energy. If two substances of different temperatures are moved close together, heat energy from the substance with the higher temperature will flow to the one with the lower temperature. Figure 2.14. Says top in brackets. If two substances of different temperatures are moved close to each other, heat from the substance with the higher temperature will flow to the one with the lower temperature. Bottom in brackets. Heat energy is still available at these low temperatures and will transfer from the warmer substance to the colder substance. So even at minus 200 degrees Fahrenheit, the heat will still move to the object that is minus 350 degrees Fahrenheit. Because molecular motion does not stop until minus 460 degrees Fahrenheit, energy is still available in a substance even at very low temperatures. And we just saw that in the figure. A substance at minus 200 degrees Fahrenheit is placed next to a substance at minus 350 degrees Fahrenheit. As we discussed earlier, heat travels from hot to cold. So heat travels from the warmer, minus 200 degrees Fahrenheit substance to the colder, minus 350 degrees Fahrenheit substance. Most of the heat energy used in homes and industry is provided from fossil fuels, but some comes from electrical energy. As shown in figure 2.15, electron flow in high resistance wire causes the wire to become hot, thus heating the air. So this is figure 2.15, an electrical heat air stream. The heater coils. A moving airstream is then passed over the heated wire, allowing heat to be transferred to the air by conduction and moved to the heated space by forced convection, the blower. 2.10, energy and magnetism. Magnetism is another method of converting electron flow to usable energy. Electron flow is used to generate magnetic fields that are, in turn, used to turn motors. The motors turn the fans, pumps, and compressors that ultimately move air, water, and refrigerant. In figure 2.16, an electric motor turns a water pump to boost the water pressure from 20 to 60 psig. This is 2.16. Electrical energy used in an electric motor is converted to work to boost water pressure to force circulation. The motor is 230 volts. The water flows in at 20 psig, goes through the pump. Goes through the water pump and comes out at 60 psig. This takes energy. In this case, electrical energy is converted to mechanical energy that is used to pump the water. The preceding examples serve only as an introduction to the concepts of chemical energy, heat energy, and electrical energy. Each subject will be covered in detail later. For now, it is important to understand that all heating and cooling systems require energy. 2.11. Purchase of energy. In most cases, energy that is purchased is done so as either a fossil fuel or as electric power. Energy is normally purchased by the unit. Natural gas, for example, flows through a meter that measures how many cubic feet have passed during some time span, such as a month. Fuel oil is normally sold by the gallon, coal by the ton. Electrical energy is sold by the kilowatt hour. The amount of heat each of these units contains is known, so a known amount of heat is purchased. Natural gas, for instance, has a heat content of about 1,000 BTUs per cubic foot. The heat content of fuel oil number 2 is about 139,000 BTUs a gallon, and 1 kilowatt hour of electrical energy is the equivalent of 3,413 BTUs. There are numerous types of coal available, and the heat content can range from 14 million BTUs per ton up to over 26 million BTUs per ton. 2.12. Energy used as work. Energy purchased from electrical utilities is often referred to as electrical power. Power is the rate of doing work. Work can be explained as a force moving an object and is expressed in units called foot-pounds, or Ft-lb. It is expressed by this formula. Work equals force times distance. Force is expressed in pounds and distance is expressed in feet. For instance, when a 150-pound man climbs a flight of stairs 100 feet high, about the height of a 10-story building, he performs work. But how much? The amount of work in this example is equivalent to the amount of work necessary to lift this man the same height. We can calculate the work by using the preceding formula. Work equals 150 pounds times 100 feet, which equals 15,000 foot-pounds. Notice that time does not factor into this calculation. Whether this process takes 1 minute or 1 hour, the same amount of work is done. However, completing the task faster will require more power, while completing the task slower will require less power. 2.13. Power. Power is the rate of doing work. An expression of power is horsepower, HP. Horsepower is the rate of doing work and includes a time element, and is expressed as foot-pounds per minute. At one time, it was determined that an average horse could lift the equivalent of 33,000 pounds to a height of 1 foot in 1 minute, which is the same as 33,000 foot-pounds per minute, or horsepower. Figure 2.17. When a horse can lift 660 pounds to a height of 50 feet in 1 minute, it has done the equivalent of 33,000 foot-pounds of work in 1 minute, or 1 horsepower. I don't see how a horse could ever lift 33,000 pounds, even to a height of 1 foot in 1 minute. anyways. This describes a rate of doing work because the time factor has been added. Lifting 330 pounds to a height of 100 feet, brackets 330 pounds times 100 feet equals 33,000 foot-pounds in 1 minute, or lifting 660 pounds to a height of 50 feet, 660 pounds times 50 feet equals 33,000 foot-pounds in 1 minute will require the same amount of power. As a point of reference, the blower motor in the average furnace can be rated at half a horsepower. If the man in the previous section took 1 minute to climb the stairs, the power used is equivalent of 0.45 horsepower, which is 15,000 divided by 33,000. Our purpose in discussing these topics is to help you understand how to use power effectively and to understand how power companies determine their methods of charging money for power. Sorry, I'm sniffly. 2.14, electrical power, the watt. The unit of measurement for electrical power is the watt, W. This is the unit used by power companies. When you pay your energy bill, you are paying for the number of kilowatt hours. It says kilowatt hours, it has the abbreviation. It's like lowercase k, uppercase W, lowercase h, kWh. You are paying for the number of kilowatt hours you used in the previous month. 1 kilowatt hour, or 1 kWh, is the equivalent of using 1,000 watts of power for 1 hour. The relationship between watts and horsepower is 746 watts equals 1 horsepower. Fossil fuel energy can be compared to electrical energy, and one form of energy can be converted to the other. There must be some basis, however, for conversion to make the cliffhanger. Alrighty. Yeah, I guess on average these videos are like 13 minutes long, so I will see you guys tomorrow.